Hi everybody, we're here with Andy Kerr of Bowers and Wilkins.
Hi, welcome.
Thank you. I'm excited to see this.
Good, well hopefully it's going to be an enjoyable experience. This is our Dale Road factory in Worthing, United Kingdom. We're producing the 800 series Diamond here. This is our flagship range of loudspeaker. It's a speaker that of course you'll have seen in Abbey Road Studios. It gets used in lots of other places across the world as well for monitoring and mastering. It's also something that if you want you can have at home, clearly, which is exciting.
Sure.
The key difference between how we approach the manufacture of this and most other loudspeakers, including some of our more affordable products, is here we're trying to take control of almost everything. So we begin with flat sheets wood. We're literally taking that and turning that into the cabinet. We're going through the whole process of cabinet construction before we even get to the point of turning that cabinet into a loudspeaker with things like drive units. Now you want to know why.
I do, yes.
It's fairly straightforward. Essentially, the loudspeaker cabinet, the enclosure as we call it, is structurally just a vessel. Essentially, if you think about it in sports car terms, it's like the chassis. And it doesn't really matter how powerful the engine is. If the chassis is not sorted in the sports car, then you're not going around the corner very quickly. The same thing applies here. This structure, this shape, is designed to essentially provide the most effective mechanical location for all of those moving components, those drive units. And the more inert it is, the more structurally stiff, in other words, it is, the happier we are, because it becomes less audible. Interesting, loudspeaker is actually the complete inverse of a musical instrument. So if you think about the value property of something like a guitar, a premium guitar or a premium violin, of course they're prized because of the materials that they're made of, who made them and how they're shaped. That's because in all those cases, the wood is contributing. It's providing a beneficial influence on the overall outcome that you're hearing. In a loudspeaker, totally the reverse. We don't want you to hear the cabinet at all. So we could choose to make it from a variety of different types of material. As it is, we make it from wood because wood works very well. We're very well set up to use it and to deal with it. It provides a nice stiff construction, and obviously the outcome is, as you can also see, something that's very pretty too. Right, so when we go through here, we're going to go into the woodwork section. The woodwork section is where we require these. The reason that's relevant is because it's centrally subdivided from the rest of the factory to make sure that we keep the dust and obviously also the noise and other things going into that area. Through there, we're taking that flat sheet wood and we're going through a whole series of different processes to turn it into that loudspeaker cabinet. It will be hotter, it will be slightly noisier, as you can imagine, and it's also more humid. It's humidified to make sure that the wood doesn't dry out or crack under the pressure. So raw material is beech. Single sheet, as you can see, very pliable, in fact easy to crack as well, not particularly strong. We're using these larger sections. If I can give you that sheet, Warren, and obviously it's there, you can feel pliable in that plane, right?
Yeah.
If I take another sheet and lay it over the top in that orientation, as you can see, still pliable.
Yeah.
Now, if I take this one sheet and turn that through 90, now try.
Oh, wow.
Now, essentially all we've done is create plywood. That's fundamentally plywood. There's no
So
specific...
it's just the grain going in different directions.
Exactly that.
Yeah.
If we take those two sheets and then we bond them together, can you see this white area here?
Yeah.
That's essentially a dry resin impregnated glue sheet. If we drop that sheet between the two pieces of wood and bond them together under heat and pressure, now try.
Oh, wow.
Feels stiffer again, right?
Yeah, it's great.
So all that happens from our perspective is we build up that structure in that alternating grain orientation so we get multiple layers. This is a section through one of the smaller speakers, and as you can see, 12 layers.
Wow.
And clearly, as you can also feel, very stiff, right?
Yeah.
Now, it also has an aesthetic layer, which I'll come to later on, but structurally, that's 12 layers of wood. The larger loudspeaker, the bigger model, goes all the way up to 18 layers of wood. So now your question becomes, well, why? Why is the difference in approach?
Sure.
Essentially, the larger the structure becomes, the greater the propensity for it to bend and flex in unwanted ways. So we have to work as hard in our larger speakers to hit the same stiffness target in our smaller speakers. In order to achieve that, we have to use more material, and we'll use a greater proportion of internal bracing as well, using aluminium sections. But that's all about making sure that the big 801, which is a really substantial piece of wooden cabinet, doesn't bend and flex as much as a little 805.
And you do these multiple layers because you have more control over it. And if you just cut this out of a piece of solid wood, the grain would be inconsistent.
Exactly. Well, cutting it out of a piece of a solid wood would be tremendously difficult and very wasteful of the existing byproduct. Also, if you're wondering, well, if that's plywood, why didn't you just bend plywood? That's plywood, and we do buy flat sheet plywood because we use that for some of our internal bracing sections. but bending that, vastly difficult without it also cracking under the process and the pressure. It's much more straightforward to do it whilst it's still essentially supple, as it is there, and you can feel how supple it is.
Yeah.
And then essentially as we heat it and cure it, it becomes hard. So we minimise the risk of damage in the course of the creation process. Now, to be honest with you, Warren, we could, like I said, use other materials for this. We could use aluminium, for example, would work very well. Two reasons why. Aluminium obviously adds weight and cost, and they're quite expensive and quite heavy as it is. The other thing is we provide a wood top coat. If you look over here, perfect example right there, this is a wooden surface. Now, if you had an aluminium section underneath that wooden surface, over time, what would happen is there'd be considerable risk that the two would come apart from each other. Because wood, as a naturally occurring material, has a habit of changing and shifting over time, and it works much more effectively when it's in contact with another wooden surface. We don't want it to at any point delaminate and come away. That's why we do that. You can feel the heat coming off that. We'll go and see that in just a moment.
Yeah, I can.
So look, this is the end game. We take those sections of wood and we curve them to create this structure here. You can see this. Now, if you were to conceive of that as being a parallel to one of those longbows that you used to see in Agincourt and all that kind of thing,
sure.
Extreme high compound wood curvature producing a lot of strength. And if I hold it just there gently, can I ask you, put your hands either side and try and push it together. And now go the inverse, try and pull it apart. And you can feel how strong it is just there, right? That, of course, is still an unsupported structure. That strength is basically just coming from that extreme curvature and the form. And that's exactly that principle of the bow, right?
Right, absolutely.
If you then add more material to it, as you obviously will do, a top, a bottom, a back, and an internal bracing system, it's only going to become more stiff. And that goes back on the reason why we want to do this. We don't want this cabinet to vibrate or radiate.
Right.
The other reason why we have this extreme form and this curve is it allows us to dispense with two joints. If you think about a typical box, it's going to have 1, 2, 3, 4 corners, and therefore 4 joints. And those joints are weak points in the construction. What we do is place the drive unit at the extreme point of the curvature and as far away as we possibly can from the weakest point of the structure, which is the joint system at the back. We've got to have a joint somewhere because we've got to open the thing up and get inside it. So we have to have this. But what we also do, as you can see, is minimize the distance from A to B. That extreme form here is there not aesthetically, but otherwise if it was parallel sidewalls like that, that span from there to there would be that much wider. By reducing it like this, we reduce the distance and that allows us to create an even stiffer construction. Now, having said all that stuff about stiffness, as you can see,
Yep.
we've machined out a couple of holes. Because we have to do that because we've got to put drive units in it.
Absolutely.
So that essentially means what we've just done is weaken our structure. So what we do is put in an aluminium plate. So that aluminium plate slots in into position in there, as you can see. Now the outcome of that is we put back that structural weakness by putting in a different material that gives us that strength back in the enclosure. We don't need to do it everywhere because here's strong. We haven't machined a hole here. We only need to put it where we've machined that hole. Make sense?
Yeah, yeah.
When the top plate comes in, that'll be aluminium too. When the back comes in, that's aluminium too. So we're using aluminium to, as I say, reinforce on top of what we've already created. Now, you know your music.
Allegedly.
If I hold this here, could I ask you just to put your hand there, just at the bottom, just gently. Now you'll feel the vibration traveling down the length of wood, right?
Yeah, yeah.
Because at the moment, this is an undamped, uncontrolled piece of wood.
Yeah.
So it's behaving very much like a tuning fork.
Right.
Any energy or impulse going in here is radiating down the length of the wood. The longer the piece of wood, the greater the intensity would become, like a tuning fork. What we do is brace that internally with these cross sections here. You can see those, right?
Yeah.
That's where this comes in. So we create an interlocking system that turns that long, unbroken piece of wood into these small compartments that you can see here. And as you go through that, that means essentially the energy only has the ability to go so far before it's damped, so far before it's damped, so far before it's damped. Make sense?
Yes, absolutely.
So the outcome of all of that is when you get to one of these. So this is now a complete structure, braced internally, aluminium plate inside, top and bottom and back in place. Pop your hand there for me again.
Yeah.
And now you can feel an inert structure, right?
Yeah, absolutely.
Hello, mate. So that's all structural stuff. We'll go around in just a moment to see how it's made. The last thing we want to talk about is the finish, what you actually see on the product. Now, as you can see, we have wooden finishes and we have painted finishes. The painted finish is essentially the kind of stuff that you'd put on the front cover of a magazine. So it's high quality paper stock, lining paper. It's all put in and bonded in the first initial construction process, as you can see by the ones behind you. The reason for doing that is essentially because wood grain has its own variability. What we want to create is a nice uniform surface onto which to paint. So all we do is put that on there and that gives us that smooth finish. Just because you see lots of these, it doesn't automatically follow that they're all going to be white speakers. This is essentially the raw material, the substrate.
Okay.
They could be painted any colour, but that's what we're painting onto. Think about like lining paper in a home when you're doing decoration. However, if we're doing wood veneer, of course it's very important to get some high quality wood veneers going on. Now, if we said to you, we're going to sell you a pair of walnut loudspeakers, and one looked like this and one looked like that, well, technically that's correct,
Yeah.
but you'd be quite upset.
Right.
So what we do instead is we book match our veneers left to right. So as you can see, all the patterning and everything else lines up. Same with this pair here as well, see? So if I do that, and then draw it back, that's a pair of book matched loudspeakers, right? Book matched, obviously, because it opens up like a book. So what that means is the walnut loudspeakers are built as pairs, and they will travel around the factory just like these guys behind you as pairs. That's one pair, this is another pair. The painted cabinets can be single right up to the point where they get packed into the box, and at that point they're made pairs. Clearly, because this is unique and it's identifiable and it's matched to this one and only to this one, that does mean also in the course of the manufacturing process, if unfortunately an accident happens and there's damage to this one, there's damage to both of them. What we'll do at that point is we will take off the wood veneer and we'll repaint them. We'll turn them into gloss black cabinets. We don't want to scrap anything at this point. Okay? Right, what we're going to do, come back to these in just a moment. We're going to pop round the corner and go and look at the forming presses, okay?
Fantastic. Sounds great.
So look, we've got multiples of these forming presses. There are 3 smaller ones. There'll be another one actually slightly bigger and more powerful than this one coming in just down there. This is the biggest one, which is designed for the largest loudspeakers. It works in a combination, as you can see, of power, hydraulic power when it's pressing, and heat. So the metal plates are heat zones, which we heat up to activate the glue.
Yep.
Well, it's a resin-impregnated glue sheet. You can see these heat zones just over here showing the temperature displays.
Yep.
And the temperature displays are running somewhere between 138 and 139, as you can see there. That's degrees Celsius,
Yep.
not Fahrenheit, to give you a sense of the heat that's required to activate the glue. Very hot, yeah. Hence the fact also that we humidify the environment. You can see the dispensers just up there, making sure that this stuff as it sits here doesn't dry out because it's being in close proximity to heat. Then of course the power comes in. Now this one is actually, this is geared back, isn't it? It could do more, crushing a car easily kind of power. Sitting under the combination of that heat and that power depends on the numbers of layers of wood and the size of the cabinet. On these bigger ones, you're in the world of around 25 minutes. On the smaller ones, it's a little bit less. It varies essentially on the numbers of layers of wood that we've got to get through and the overall size of the cabinet, because that relates to the overall amount of power that's needed to bend the wood. Essentially, once it comes out from one of multiple presses, it will sit there for a period cooling off because it's still very hot to touch at that point. What we also need to do is insert, you saw them in the ones around there, these get slotted in place inside. The reason at the moment is the wood's maintaining or retaining essentially a heat memory, and it's wanting to continue to try and close up. And of course we can't have it close up too much because then the guys can't open it up and put anything inside it. So these simple spreader plates just sit inside while it cools off, make sure it doesn't go too far. If you're interested in engineering and stuff, and I get the sense that all you guys are, this is like almost like the antipode of some of the other stuff that you'll see later on. This is like almost, I don't know, Victorian, heavy duty kind of stuff, isn't it? We're using big, powerful, heavy hydraulic presses to bend and crush things, you know. Whereas like elsewhere, there's like teeny tiny Chris Wass precision. It's tiny things, you know. So
Yeah,
it's a really interesting tension between the two approaches. So this sheet he puts on here is just protecting the wood.
Yeah.
Essentially, we don't want to impregnate any dust particles into the wood veneer. So the protective sheet, and then you'll hit it with an air blast to just make sure it doesn't get anything going onto it. Yeah. It's the residual sound that always makes me laugh as well. It's like the sound of the Titanic deck cracking. You know, you can hear that kind of, that's wood under a lot of pressure.
Oh, wow. Oh, yeah.
And you can feel the heat as well, yeah. As I say, this is why I had you guys take all your jackets off and stuff, right?
Yeah.
I mean, we've got AC fighting as hard as it can, but this is a hot place. So this, but anyway, that's the process. Fairly obviously, this is all bespoke, right? I mean, the wood bending machines themselves are not, the tools are. So we don't want to be changing this every 2 weeks. You know, this is something that needs to last. You tend to find that the fundamental cabinet form is going to be in the market for somewhere between 5 and 10 years before we think about changing it. We might change design detailing around the top of it, you know, colors, finishes, leather, that kind of thing. But actually how we make it is going to try and have some legs, because every time you change, you've got to change all of those tools, all those forms, and then you've got to prove out whatever it is you're doing next, right? They all have these different recipes. You can see over there, 804 walnut wrap recipe on the sheet just there, right, Chip?
Yeah.
So that refers to numbers of layers of wood, how long it's going to be in there, what the temperature is, and so forth, right? There's subtle nuances either way, but as I say, different ones are required and different recipes are required depending on the model that we're working on. All right?
And that's this?
Yeah, that's one of the larger ones. So these are 801s. That will mark up your fingers at the moment because they've been wet and dry sanded, but yeah, they're 801s. These are the ones that are in Studio One. So we've made our wrap form.
Okay.
We're going to go back round the corner now and see the bots in action do some of the cutting. So you'll have noticed when he dropped that into the press just then,
Yeah.
he could put it in relatively quickly. He didn't have to spend a huge amount of time lurking underneath it to kind of center it and get it absolutely A1. Now there's a reason for that. A, it's a hugely powerful press that if things went wrong could potentially do damage, and B, it's very hot. So you don't want people spending more time than they need to trying to center something up and precisely work on it. So they're working to a reasonably substantial amount of float or excess in the wood. That's much more safe than getting it really, really precise. This is where we get really precise. So that wrap form that you saw over there is now sitting in the tool, and the tool will machine away the bottom and the top and the apertures for the drive units. And then as you can see, they take the tool, take it out, invert it, and it will machine away the back. So on your left is stage 1, and on your right is stage 2. You got it?
Yeah, yeah.
Now, if you noticed at the edge of the wood, as you can see there, before it's been machined away, it looks like there are some gaps in the spaces between the wood. Give me another example. You can see from that one there, right? Now remember, this is right at the limit of that piece of material, and it's under a huge amount of pressure. Now, if you took a stack or a sheaf of A4 paper, put it down, put your hand right in the middle of it and pushed, of course the edges of it would flare up and open, right? This is the same thing happening here. You don't have to go down very far at all, if I flip that over, to get to fully joined with no gaps of any kind, yeah?
Yeah.
So again, that's the target, and that's what you can see right in front of you in those two units there, yeah? Now clearly all of that excess wood is going to be recycled.
Oh, it is?
Absolutely, so it's taken away and used as energy for fuel, fuel energy for wood, pardon me, so we take it to a power station in Shoreham Seafront and it's used there, alongside the sawdust, which is also vacuumed up and used there as well. So
Right.
as much of the waste product that comes out of this process as we can, we are looking after and recycling.
Fantastic.
Now, the robots themselves are obviously hugely important to the outcome here, and I think it's worth emphasising. I think to some extent there's sometimes a misunderstanding or a misconception about the notional aspect of craftsmanship, about what that means. We clearly are working to a level of repeatable quality, which is quite high, in our opinion. The most skilled craftsperson in the world will eventually get tired, might occasionally make a mistake. I think the perfect allegory for that is Rolls-Royce, where you see those great stories about the guys kind of hand painting the swage line along the side of the car, and it looks incredible. Those guys aren't stamping out wings or bonnets on the sheet press. That's done with a robot. We're the same, if you see what I mean by that. So where it requires sub-millimetric precision, and it requires that each and every single time, you use a robot. Where you're looking for the final details, you use a person. And as you go around the factory, you'll see that all the way through. The machine with a human operator working together. So right now, this is going to be cut to a tolerance of plus or minus 0.2 of a millimetre, which is pretty precise. But remember what we said before, the structure has to join up precisely all the way around. All of the elements of it come together to create that complete assembly. Any weaknesses or variations are like cracks in an egg. No good to us. We also can't have any air leaks, because an air leak's like drilling a hole in the side of a trombone. So sealed, properly structurally sealed, is hugely important. If you look just behind you, Warren, you can see exactly that in hand. What's going on here is that process of this is then being checked and validated to the drawing by one of our skilled operators. So essentially, it'll come out of there, and then every aspect of it is checked there before it moves on. The reason why that is also hugely important is because at this point in time, it's just wood. So of course, it's relatively straightforward to recycle it. Should it be the case that we send it around the factory and apply a lot of paint and process and time and effort, and then discover there's an issue, A, we've made it much harder to recycle, and B, we've wasted a lot of time and money. So take the time now, get it right now. So you can see over there it's machining the tops. The tool that it's using right there is being constantly monitored for sharpness. So there's a, if you look to your right, Warren, through there, there's a, what looks like a white lit door with a black surround, just over on the right-hand side. Do you see that there? That one there? That's where the tools live. So essentially there's a rotary dispenser drum, and once it's completed its task, the bot will go over there, the door will open, out will come the next tool for it. It will drop off the one that it's used and pick up the next one. There we go, in action right now. That was well timed. Funny, isn't it? Everyone loves a robot. As it comes off there, and after you've machined it away, the next thing we need to do is obviously open it up and put something into it. So this tool right here is called a spreader, and what it's going to do is go over the sides of the cabinet like this, grab hold of it, and then pry it apart. There's a crank handle down that side that allows you to sort of wind it to a dead stop, and that means you can cope with that power, because you felt that already, right? There's no way I'm doing this by hand. This needs to be pulled apart, held open, and once it's held open, the guys can slide the internal bracing structure into the loudspeaker. They're going to use a glue dispenser just to put glue into all the slots and grooves. And then this thing that's over here behind you, Warren, just behind your back there, is going to be slid into position. So that's the internal bracing system. Remember I spoke to you before about the flat sheet ply. That's machined away. We'll see that in just a moment. These notches here correlate to those grooves and slots there. So this is the front of the loudspeaker. And then obviously the drive units are going to go into that position afterwards. So that'll go into there. At that point, just reverse the tool. So rather than pulling, we're now pushing. So if you look at this one, it's got that bracing system inside it. That's the back of it. And then that's the bottom of the loudspeaker and the top of the loudspeaker. It's going to sit like this under pressure for about 2 hours. Well, not for about 2 hours, but 2 hours. And then when it comes out, it will rest like that for a further 2 hours. At that point, it's done, and we now can't take it apart even if we wanted to. That's why it's worth taking your time up here to get this stuff right. This plate here is steel. It's not aesthetic. It's not something you'll see later on. It's called a setting jig. We're pushing really hard now. The tool's reversed. So rather than pulling really hard, we're pushing hard to make sure that all of that adhesive dries off correctly. We also don't want any air gaps or bubbles in that adhesive. So the more power we apply, the more effectively it dries. As a result of that, there's risk that this wood could bend up too much right at the back, and we don't want that. Later on, a much more attractive component part's going to go here, which essentially houses the brain of the loudspeaker where the crossover components live. And what we want is for the customer to be able to take their thumb and run it down the edge like that and get a nice, smooth, consistent transition without any sense of a step or a gap. So this is sitting here right now just to essentially preserve and manage that edge so that when it comes out, it feels like it should feel. So two like that, and at that point, we've made a complete cabinet. Now remember, these are pairs, as we said before. These are all 803s. What we try to do is group the workstations in areas that make sense. So the tool that's cutting them is there, and then the assembly area is literally right next door to it. The smaller one over there is making the 805. So again, the guys aren't having to carry this over long distances to get from one to the next to the next. The largest, heaviest loudspeaker that we make, the 801, is right down that end of the factory. And the reason for that is it's the biggest, heaviest thing to carry around. So we want to minimize the distance from it to the sanding and painting, which are that end of the factory. That's why it's down that end. Okay.
Fantastic.
So this tool here is taking that flat sheet ply and machining it away. So it's a simple 2-axis tool, unlike that one over there, which is a full 5-axis with like a robotic arm. This just works on 2 planes, that plane and that plane. It's a vacuum table, so the wood gets sucked down onto it, and then from there they can machine it away. So there you go, perfect example, flat sheet wood, machine surfaces, you can see how it works.
I've been to a couple of factories that build cabinets. I've never seen anything this intense.
No, well, no.
Insanely intense.
You won't have done.
Yeah.
So in just a moment, we're going to come and have a look at the painting process, but before we do that, we're going to go into this end over here and have a look at sanding and sanding preparation. Every single cabinet's going to go through here at least once, and obviously that's the key to getting the right finish before we go and start putting paint on. Okay, so if you look just down there, spinning, literally as we are, you're going to see it go. Let's go straight in. Right, don't go too far in because there's a light beam here and it won't start. If you look past this big cabinet on the other side, you can see that robot arm doing things.
Yeah.
So this is basically taking care of most of that first finished quality. The guys here, the guys here then can really focus on the detail stuff. So if you just took a standard cabinet and applied paint and left it, you'd get a surface finish which has a series of surface imperfections on it that look a bit like the surface of an orange. We call it the orange peel effect. Obviously it's not orange, it's black, but you can still see it. What we're going for with our black cabinets is a piano gloss black finish. So in the case of those cabinets, they're sanded once. Remember, that's with that white paper finish to create a smooth surface. From there, they'll go back to the painting area and they'll receive 5 coats of base coat paint. Now those 5 coats of base coat are of a sufficient hardness and thickness to give you the density and the quality of the finish, but by their very nature, they create that orange peel kind of effect. What the guys will then do is bring them in here and give them a second sand. And that second sand is what creates what looks like a grey loudspeaker.
Right.
So that one that you touched earlier on that was very smooth, that's one of those. So what that's doing is removing that stippling orange peel effect from the surface of the paint. When that's done, they'll go back to the robot and they'll receive 4 top coat. The paint formulation for the top coat is different from the base coat, and it's got less propensity to create that effect. Once that's hardened up, they then go and get machine polish. So the black cabinets are several stages. First sand, first paint, second sand, second paint, machine polish. And in terms of duration, it can be as close to 2.5 weeks, because there's lots of periods of time between each of those steps to allow the paint to harden up and to cure up correctly.
2.5 weeks
Yeah,
to complete the paint?
for the black ones, yeah.
Yeah.
The wooden cabinets are a great deal quicker. All they require is that first sand. In the case of our walnut finish, they then are literally 2 coats of lacquer and they're done. They're really quick. We make a finish for Asia, which we call rose nut, which is the walnut hit with a little bit of red. Tends to be more popular in that part of the world. So in that case, it's relatively quick as well. Hit of red, couple of coats of lacquer, done. And then we have a satin white finish, which is mostly more popular in Northern Europe, particularly Scandinavia. But it's a satin finish, so it doesn't have any machine polishing. Ends of the scale, walnut that end, black this end. Now, the bot is very clever. Again, if you've ever sanded a wooden floor, you'll know how horrendous that job is and what it does to your forearms and all the rest of it. So the investment here is to create a very smooth and consistent amount of pressure. What it's doing is working to a set of pre-programmed, predefined coordinates. So, for example, the guys setting it up will tell it the size of the cabinet that you're working on and the task. And the task would vary. You'd use a different type of sandpaper grit on a wood veneer as you would on working to rework paint, for example, because you don't want to take off that wood veneer. The second part of the job, though, is it's constantly monitoring what it's pushing down onto. And the reason that's relevant is because there are holes in the front of these things. If you're pushing on a flat surface and then you get to a hole, almost inevitably what normally would happen is you'd roll off into the hole. We don't want that. We want a nice smooth surface without nice sharp edges. So the bot monitors what it's pushing down onto and what pressure's coming back up to it, and it can stand right on the edge of a hole without rolling into it. And it's that gives us these really sharply defined transition edges. At the end then, what the guys will do is, as you can see, take it off the bot and check it. So again, it's still that symbiosis of human operator working alongside machine, but the key advantage is they've not had to do this all day long for 6 hours, which, as naturally as skilled as a person could be, will lead eventually to pressure marks, swirl marks, and those other things. So the outcome's a much better finished product. Okay? So look here, if I can show you, that's a perfect example of what, see that surface stippling?
Yeah.
Yeah. That's the spray.
Yeah.
So this is before and this is after. That will have a grit effect on it and when you run your finger, but you see how smooth it is, right? So these turn to that, that's cleaned down, and then top coat goes on top of that, okay? Draw your attention to these over here. Remember I said we don't want to be scrapping anything. So these come with a fault sheet. The guys are taught, if you can see an issue, a mark, a flaw, a problem, reject it. None of these are going to go in the bin. They're all going to be reworked through here because we've got the capability to do it. Of course, the fact that they've got paint on them actually makes it much harder to recycle them successfully anyway. So we want to save them. It's in our interest to do so. So if they can see a mark or a flaw, they highlight it, we bring it back in and get it done, get it reworked. There's no defined, if you like, tolerance sheet for what that mark or flaw could be. If you can see it, it's a flaw, deal with it. Now on your left, Warren, you've got a giant loudspeaker rotisserie oven. If you put your hand on the glass, you can feel the energy coming off it. We're baking in there, and you can see the conveyor belt is moving the product through, and as they go through, they turn slowly. They're about 45 minutes cycle time in there, and when they come out into free air, we're going to clean them, and then they're going to go into the chamber ready to be painted. Again, everybody loves a robot. So we paint by batch. So as you can see, these are all white cabinets and they're receiving white paint. We don't go, one black one blue one, whatever else. The reason for that partially is, of course, you want to avoid paint contamination. So for the white finish, it's hugely important that you've got a highly clean chamber. You haven't got any risk of any small elements of other kinds of paint inside the paint lines, the nozzles, the leads, and so forth. The guys come in on a Sunday, they do a deep clean, decontaminate the whole place, clean it all down, reline it. As you can see, it's all relined. And then we paint white on Mondays. It's always white Mondays. Truthfully, not that it would happen, but you could probably get away with a very small amount of white paint contamination in something else. You could never get away with a small amount of black contamination in white. So start with white and then go from there. So once this is done, they'll clean down, clean the nozzles, clean injectors, clean the chamber, and then we'll go on to a different finish. Now we can do by hand as well, but that's done upstairs. So if you decided that you wanted Ferrari red, for example, it could be done, but it will be done in a different location. Here, this is building to stock, right?
How many stock colours do you have?
4. So a white one you can see there, a black, the walnut, raw walnut, and a rose nut, which is that red hit colour. That's sensibly more. It's interesting because intellectually, you always imagine that there'll be more interest in interesting colours. Just it seems like the right thing. The reality is, almost always when you try it, the customer goes, yeah, that's very nice, and then they go and buy the black one. So over time, we've gone very broad with colour spectrum and brought it back to, no, we have a relatively controlled range of standard, and then if you are that one or two individuals that wants the wacky, we can support you, but we'll do it as a custom finish.
I see.
Okay?
Marvellous.
So 45 minutes each time through there. As you can see, the paint application itself is pretty quick. Round it go, round it go, round it go, and then it's done. And just for a bit of context, I mean, you can see what they are, right? They're all 801s.
Right.
That's a big loudspeaker.
Very.
Now, if you think about how many you can see, gives you a context of the kind of scale of the operation. We didn't just set those up just because you were coming.
So you're selling a lot of them, is what you're saying?
Yeah, it's doing pretty well for us. Interesting, actually. So look, quick reminder of where we came from. Flat sheet wood at the start.
Yeah.
Finished cabinets, ready to go and receive more at the end.
Marvellous.
We're going to go out the noisy space now. I think it's like you were saying before, guys, right? I mean, conceptually, people don't necessarily fully appreciate the scale sometimes.
Right.
I know that there are significantly larger factories in the world, but in terms of manufacturing for large high-end loudspeakers, this is pretty big.
Absolutely, yes.
So, this is Diamond Dome territory, right?
Diamond Dome.
Yeah, palm your hand.
Yeah. Oh, wow.
So, again, I can say the words tweeter to you and you'll understand what I'm talking about, which is such a blessing for me. Normally I don't have that conversation luxury. So this is a tweeter. Obviously it's designed to move at very high frequency and to stay in shape. It is a 40 micron and it's 88 milligrams in terms of mass. So it is diamond. It's not just a name. We're not just saying it to be flashed. Shall we have a go? Nothing really there, right? Sorry, thank you. Put it on a wire because it's a lot easier for me to handle it that way. It's phenomenally fragile. It's basically a bit like a piece of eggshell. Now, the principle. In any loudspeaker that involves a tweeter, the dome is going to be moving very rapidly. Mm-hmm. The upper limit of what you can hear is 20,000 cycles, or 20 kilohertz, 20,000 movements per second. If you just design a dome to only approach that threshold point and no more,
right,
then as you get close to that point in frequency, you're putting a lot of energy into a system which is stressed. It's a bit like designing a car that can only do 100 kilometers per hour and then trying to drive that car at 95 kilometers per hour. And you can imagine the driving experience, right? The engine screaming and the car's pouring smoke and you're weaving across the road because you're right at the threshold limits. So what we found over the years is if we push the audible threshold point and go beyond it, then in the audible range where you can hear, you're creating something that's operating very benignly. And to go back to the car analogy, you're creating a Bugatti or a Lamborghini or whatever it is that you fancy, a car that can do 300 kilometers per hour. And if you're then driving it at 100 kilometers an hour, you're nowhere near its threshold point and everything's completely serene. That's the simple logic behind it, right? So we use different materials. The more affordable loudspeakers use aluminium, and that allows us to hit 38 kilohertz. Our middle tier uses aluminium reinforced with carbon, which allows us to hit 47. And these use synthetic, artificially grown diamond. And that allows us to hit 72,000 cycles per second, which is more than 3 times beyond the point where you can hear. Now, these are the ones that you find in Abbey Road Studios. Just to be really, really, really clear, no one is claiming that you can hear anything in that range. Buying a pair of these speakers does not turn you into a bat. It just means in the range where you can hear, it's as stressless as any moving component part could ever be. That's the principle. And it's that gives you that accuracy. Because distortion, I mean, obviously it's a very commonly used word, but fundamentally it's literal. If the cone is moving or the dome is moving in such a way that it's physically, as it's moving, distorting its shape, then the sound that it produces is distorted. It's as straightforward as that. So the more stiff this is, the more it stays in shape, and the more it behaves how we expect it to behave, and the more you hear what you should hear. Of course, diamond is wonderful for that because it's highly stiff. Of course, it doesn't naturally come in those forms and shapes, so what we do is we grow it. So a substrate, a shape like that, is put into the bottom of a reactor by a company called Element 6 near Ascot, part of De Beers Group. And they'll superheat it and pressurize it. And when I say superheat, I mean like volcanic temperatures. Then they inject a gaseous cloud of particles containing carbon into the top of the chamber. And then over the course of about 6 hours, they gradually reduce the temperature and the pressure. And as they do so, the carbon particles begin to descend. And as they begin to descend, they chemically change in state from carbon particles to diamond particles. And then they form over the top as a very thin membrane. That's actually what it looks like underneath. And as you can see, it actually looks carbony, but it's not. Chemically at this point, this is diamond. Just to give it a kind of uniformity and frankly a more overtly diamond look, is then given an overall top coat of platinum. And that's what gives it that final look and feel. That has no acoustic benefit or change. It just makes it look more like what people expect diamond to look like. But nonetheless, acid eroded this away, so this comes off and we're left with that thin membrane. Laser cut the edge to get the shape, and that's what we've got. And the performance speaks for itself. And again, this is why it's so highly valued. There's a great true story going back in 2005 when we'd first done this and we introduced a pair of 800 diamonds to Abbey Road Studios. Got a call from the guy saying, you better come up, there's a problem. And we're like, what? We went up there, listened, couldn't hear anything. And they said, no, we can hear this ticking thing. So we actually uplifted the speakers, brought them back, measured them, checked them, they were completely fine, returned them and said, no, they're completely fine, they're doing what we expect. Well, we can still hear this ticking. So we went up again and asked them to play it back again, and we heard it this time, and you could hear this very faint kind of, it's really faint, just in the background of the recording. And eventually we worked out that it was actually on the recording, it wasn't the speaker, and it was the cufflinks of the pianist.
Oh, wow.
And it hadn't been picked up before by preceding versions of our own loudspeaker because they hadn't had the resolution to pick it up. So that's the essence of it in a nutshell, really. It's the closer you get into what's there, ideally from our point of view, the more ideal the performance is. And this is the key tool that helps us to do that. It's very exotic. It only gets used in a limited number of products. You can't have it in the affordable things. It has a significant cost, as you can imagine. Quite complex to make, as you can see.
Right.
But it arrives to us in a sheet like a box like that. As I say, it's made for us up the road. It's our IP, but we haven't got a reactor here, for obvious reasons. So it's got a sort of soft coating there, if you feel, which just protects the dome, keeps it in position. That means you can rattle it around and it's not going to have any harm come to it. And then the guys go through the whole process of building it up. Do you want to go down and capture some?
Yes, absolutely.
This is a different dome that we're making here. This is a larger one, but anyway, dome there. Surround goes on.
Is that a diamond dome as well?
No, it's a different one. Actually,
okay.
We're making CT ones there. This is for our custom theatre range. In position. This is a diamond dome. There you go. In the coil. See the movement? Very small
Yeah.
movement. And there's the coil there that I had you held earlier on. You see how carefully I'm handling it as well. You have to be.
I'm not going to touch it. I don't want to break one of those.
No, they're quite dear.
Yes.
Magnet motor system as you move around, and then we get to a point at the end where we've got a complete one. You can see a complete one just on there being tested. KC, could I just have a quick look at that one, please, man? You trust me? Thank you. Sorry.
It's okay. I'll about to fix it. The last one's been naughty.
It's crazy looking. It's almost like it's inverted. It's concave and convex at the same time, depending how you look at it. Does that come across in the camera?
Yeah. The light path, I see exactly what you mean as you
So
move.
is it concave or is it convex or concave? It's very surreal.
So each one of these, as you just saw, is going into there for test and measure, and literally, as you saw, one of them's actually failed, which again is honesty in action, right? We test
Sure.
each one before they go downstairs. If it fails, they will resolve it, they will get it fixed, and when it gets fixed, it will go downstairs, but it doesn't go downstairs until it's past that end of line test first. Again, I mean, it's pretty straightforward, the reason why you want to do this. You get to a point on the production line, the guys need to be able to put something together relatively rapidly with a degree of confidence that everything that they're putting into the loudspeaker is going to work. So you test everything before it gets to that point of final assembly, and in the final assembly line, all the relevant bits have already been evaluated by the teams elsewhere, so that it all comes together quite fast. One thing I want to draw your attention to is this. We spoke a bit when we first met about the Nautilus and the Nautilus cabinet. In the 800 series, this is how it's executed.
Yep.
And you can see exactly the same principle. And if you look down the length, can you see a hollow tube? Yeah, running down there?
Yep.
So the diamond dome, living there at the end, on that section that I held in my hand just now, as you might have noticed, it had a screw thread. That screw thread is the bit that goes into there. And then the energy from it is dissipating down that tube length, just exactly like it would do in a Nautilus. This is a higher mass construction than a Nautilus. This is machined from a single billet of aluminium, so it's a single construction. Very highly stiff. Principles are just the same as the cabinets that you saw being made next door. I hope that also answers the question about why we don't make the whole loudspeaker out of aluminium, because as you can see, just that construction requires that much mass.
Oh, yeah, it's quite a difference.
So imagine what you'd be dealing with if you were making the whole loudspeaker cabinet from something like that. Yeah, so, but yeah, milled from solid, and what it does is it gives us that tremendous holographic kind of imaging, because as we were discussing earlier on, it's reducing all the frontal area around the dome, so there's all of the energy from the dome's going out, it's not going in. If you think about it like, sorry, loudspeaker basic stuff, but if you think about it like a torch, good old-fashioned proper torch, you know, then clearly, like, the more kind of light occlusion and blocking there is in the way of the light output from the torch, the less energy from the light is going into the room. If you minimize as much material as you can around the light at the end of the torch, more of the light goes out into the room. It's as straightforward as that. So this is sized as close as we can get it to make sense of that, which means more of this is doing what it's supposed to do, essentially. Yeah? We do crossovers here as well. Are you interested in that kind of thing, or do you want to move on to
Absolutely.
drive? You are. You can
Look
see
at
the whole nine
crossovers.
yards. Simple two-way loudspeaker, the smallest one that I introduced you to at the first thing this morning when you were trying to push together.
Yep.
The 805, that's the back plate that's going to go on it, and that's the crossover inside. So this will live in that compartment space you saw
Yep.
at the back of the loudspeaker. So obviously this is a fluid-filled capacitor, so keeping it away from the air pressures inside of the cabinet is quite sensible. It also helps it to work better, but it also means from a serviceability and access point of view, if anything goes wrong, all we've got to do is remove this metal plate. And as you can see, it's got these little latches here, which are
Yeah.
accessible from here. So nobody has to take the whole loudspeaker apart. If you're unfortunate enough to have a house party and one of your guests gets overexcited with the volume, more than likely what's going to happen is that's going to pop, and only that, because that's designed to save the rest of your crossover. And then somebody can come along very quickly, take that off, put the next one on, and you're up and running in 5 minutes. So it's actually really good.
Wow.
The reason why they're called crossovers, we refer to them as filters. If you think about the full flow of the musical signal arriving into the loudspeaker here, with every element from the lowest sounds to the highest sounds, as one complete parcel of information, what this has to do is essentially filter that information out to divert it to the correct component within the speaker.
Obviously, what you don't want to do is to sell a full range bass signal into a cone that big, because it's going to go bang. So this is fundamentally using electrical resistors to allow us to filter where we send that signal and control it. Now, what we don't want you to hear from a perceptual point of view is any sense of that mechanically happening, or any sense of a gap in the signal between one cone and the next cone. So if you think about the output of the high frequency and the output of, let's just say, the mid bass in a standard two-way loudspeaker, what that's doing is adjusting the alignment of the output of those two, so that from your perception, the lower part of the sound of the high frequency crosses over with the upper part of the output of the mid bass cone, and that's essentially why they get referred to as crossovers. The great advantage that we have, as you'll see in a moment, obviously you've seen partially anyway, is we're solely responsible for the design and the manufacturing of our cones. We don't buy them in from other people. A significant number of loudspeaker brands offer it differently from that. They would buy cones from select suppliers. There are lots of companies that do it, Vifa, ScanSpeak, there's loads of them. Our perception is, or perspective is, pardon me, is that if we fully understand how the cone behaves, we can fully understand what we need to do in the crossover to naturally get them to link to each other to the best of their ability. And that means we can do it with the fewest possible components. If you go back to that one, you basically got a bypass capacitor, a capacitor, and a resistor. Pretty simple, right? As a circuit. There's no electrical circuit in the world that was ever improved by having more component parts inside it. So the simpler and the shorter this is, the more likely what goes in here comes out here to the cones. So we try our best to keep our crossovers very, very simple, but we're in the advantageous position that we have the ability to do that partially because we design the cones and the domes ourselves. Does that make sense?
Absolutely.
So the guys building them build to reference boards. These are the reference boards. They build the individual elements first and test those. It's all done by hand over there. And then they lay it up onto a complete assembly. So by comparison with the one you just saw, this is off an 801. So that's off a flagship model. Oh no. So this is a much more substantial piece of kit from a much more substantial three-way loudspeaker. And as you can see, I don't know if you know capacitors. These are some very, 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 very expensive capacitors.
Very large capacity.
Very large indeed.
Yes.
Yeah. Now, if you go to some places that work on that kind of thing, they'd use things like a hot bath for essentially soldering. So they just drop a board in, roll it through, and it comes out the other end and it's soldered. We're not making enough to justify that. Also, the individual value component of each element is so much that we don't want to risk overheating it. And also, fundamentally, the other thing we want to do is just have it looking nice. So everything's laid out so that all the lettering's in the correct orientation. You're never going to see that, but if somebody takes a press photograph of it, at least it looks smart. So it's all done by hand. So the testing area over there, the assembly area over there, pardon me, they'll build them, they'll test them. Once they're passed, they'll pack them in those black boxes that you can see there, and the guys will take them downstairs to go on to the end of the production line. So for a long time, we were associated with that. That is, we have to call it a polyaromatic aramid fibre, but you might know it as another material that's sometimes used in body armour. You could probably say what that material is, but I couldn't.
Right. Okay.
That's the one.
It ends with Evla.
That's it. The reason is we don't have the rights to use it anymore. So basically, we had the sole IP on it for 20 years.
Right.
From 1976 through 96. And then it's DuPont's material, it's not ours. And
Right.
as you know, it gets used in other applications as well.
Right.
From that period of time onwards, other companies started to use it. We, at that point, felt that what we wanted to try and do was come up with something a little bit better and see if we could develop a different way of doing things. So we worked on the principle of our own material, which we call Continuum. This is our own material. And as you can see, it has commonalities of approach with
Right.
the older generation. It's a woven material, but it's also very different in another regard. And the key difference is if I ask you just to flex that one more time, Warren, you can feel the relative stiffness of that one.
Yeah.
Okay, now try flex this one.
Oh, I see. Yeah.
You see it's massively more flexible.
Yeah.
In fact, it's so flexible that if you wanted to, you could do that.
Right.
So if you want to understand what's going on,
Right.
If you think about a typical loudspeaker cone and a more affordable loudspeaker, it's probably made of a material such as paper or plastic.
Yeah.
Now, paper or plastic are isotropic in their behavior, so they have an equal property of strength in both directions.
Yeah.
Put that into a simpler way of thinking about it and take a bowl of water
Yeah.
and then take a stone and drop it right into the middle of the bowl of water. And what would happen is ripples would propagate away from where that stone was and they'd go towards the edge of the bowl. How many and how big they would be would depend on how much water was in the bowl and how hard the stone was when you threw it in and all that sort of stuff. But nonetheless, you guess what's going to happen. Now, as the energy goes out to the edge of the bowl, it's going to meet the edge of the bowl and some of it's going to start coming back. And that's because water has a relatively equal property of strength in multiple directions. So the energy goes out, hits the edge, starts to come back, right? You've seen that in swimming pools where waves rattle across that and they hit the edge and they start to lap back in. It's the same thing. So that's a really simplistic way of expressing how sound behaves on a cone made of plastic. Let's turn that stone into a single click. The sound radiates outwards as a circular waveform from where that click was, along the surface of that cone, until it gets to the edge. And when it hits the edge, some of it starts to come back. Okay? Now that's unwanted, that's noise, that's reflection of a direct sound. Now all we've done there is put one direct sound in. What happens if you put in two? 1, 2. The first sound goes out, hits the edge, starts to come back, and as it starts to come back, it meets the second sound on the way out. So you've got the reflection of energy meeting the direct energy on the cone at the same time. And that's noise. The reflected energy is the noise getting in the way of the direct second signal. So woven materials are great because they behave differently. They are anisotropic in their behavior. So as the energy goes out towards the edge of the cone, it essentially comes back and gets ripped up into fragments or smaller portions or sections by the different directions and orientation of the woven material. So it doesn't stay as a perfect circular reflection. Some of it will travel down here, some of it will travel down here, and so on and so forth. So the noise is still there, but it's no longer that perfect circle. It's much, much smaller fragments or portions of that circle. Make sense so far?
Yes. Yep.
So the great thing about this material, which we've developed, is it has an ability to control and optimize how that energy reaches the edge of the cone. It works on a principle of carefully controlled damping. So as the energy goes out, we're essentially, metaphorically, gently applying the brakes as it approaches the edge of the cone by absorbing it using damping. As a result of that, significantly less of it hits the edge of the cone. As a result of that, significantly less of it wants to then come back towards the middle of the cone. And that which does come back is then broken up in the same way as before by the directions of the woven material. So the outcome of all of that is this behaves significantly cleaner with less unwanted noise than this. And as a result of that, you hear more, because you hear more of the direct intended sound rather than the unwanted reflected sound.
Marvellous.
So we call it continuum, as you can obviously gather because we're all nerds, but partially because it's also like a continuum in space.
Okay.
So as the energy goes out, it's essentially like it just keeps going,
Right.
rather than having something to hit and bounce back from. So we're very careful about it, we're very protective of it because it's our tech, fairly obviously, hence the fact that we don't fully reveal the process, and we still haven't fully revealed the process. What the raw materials are involved, we're not going to share, sorry. How exactly we make it, we're not going to share, sorry. The important point to understand is you can't buy this from somebody else, and we don't sell this to anybody else. This is our little game changer, and we're deploying it in as many loudspeakers as we can. Beyond that, we also have base cone. So, base cones can get quite substantial, they look quite big. As you can feel though, not necessarily as heavy as you would think.
Oh, no.
What we've got here is a very highly stiff construction, which is a composite. So it's 2 layers of carbon fiber encapsulating a foam core. If you look at it through the cross section, you can see. So the foam core has a variable curve profile, and you can see that foam inside. The foam is called a syntactic foam. It's the kind of thing that gets used in things like helicopter rotor blades. So it's very light. But as you can see, by encapsulating it, we get this very strong, stiff structure. So give that one a bend.
Yeah.
and you'll be a while. It will go eventually, just so you know.
Yeah.
But it feels pretty stiff, right? This is back to the same principle as the diamond dome. So this is the idea of a pistonic dome. Rather like we were discussing earlier on when we first met, the Nautilus, all 4 cones and domes in the Nautilus are of the same material, behave the same way, and are all pistonic. So they all work in that idea of not bending and not flexing. But that requires 2 mid-range cones, the upper mid-range and that lower mid-range, if you remember from the Nautilus. In an 800 and other speakers, we'll cover the mid-range area off with a flexible cone. The reason that's advantageous is it allows us to use the same cone type on a loudspeaker that's relatively small or a loudspeaker that's very substantial. It's very difficult to scale the technology of the Nautilus into a speaker that's this big. Whereas this, you can have that cone play a very significant portion of sound because it's capable of playing a very significant portion of sound, including, relatively speaking, quite deep sounds because of its flexibility. So it would be teamed with something like this and obviously a diamond dome above to create the full flagship 801. Does that make sense?
Yes.
All right, so this is where we assemble all the drive units together. So you've got the cone, in this particular case, the base cone that we saw from before. And what we need to do is turn it into the complete assembly. And these are all the constituent elements that are going to go into that. So you've got the chassis, or the basket, which provides essentially a mechanical location point. You've got the voice coil with the spider, which provides the assembly. This, of course, attached to this, and then essentially fed with energy from the magnet, is basically the bit that's making the output. It's going away, coming back, going away, coming back. Magnet and pole all laid out here as well. This is quite substantial. This is what we call the anti-resonance plug. This slots through that into that. Now there's a reason for this. It's foam, as you can feel. As this is moving more and more and more, it could have the ability to do that. Do you see? Go slightly out of round because of the force that's going into it. What that does is it provides essentially a low mass brace, so it sits inside almost like a finger on a wedding ring. And as a result, it's providing sufficient energy to maintain that in shape for as long as possible and push away the moment when it first starts to do that. It's going to do that at the most extreme volumes, the most extreme frequencies, because it's moving the most. Don't forget, these things have got the ability to move quite a lot. You can see the energy being pulled onto the spider by doing that, right? And the more that's doing it, the more that's potentially going to happen. Now, we spend a lot of time not only working on all of these different elements, but also on the motor, the magnets that go into the complete system. The reason that's relevant is you want to be able to accurately control how rapidly this moves in response to a signal. But just as importantly, you want to be able to control how accurately it stops. If you think about it in the context of a 1970s American car, when you pull up at the traffic lights and you brake, and it just sits there gently rocking on its springs for the next 30 seconds, because it's got a huge amount of mass, and that change in inertia means it's still kind of wanting to go, and it's not particularly well controlled because the springs are very soft, and it just sits there rocking. If this is sent away very rapidly, but then we don't control how it stops, then the energy comes into it, and it's just going to go like that. And as a result, you won't get that impact of a transient. What you'll get is rather than, which is what we're looking for.
Sure.
So to achieve that, we use neodymium. So very highly powerful neodymium magnets and motors. I'll keep those ones well away. So this is the kind of thing that you would use in an electric motor in a car these days as well. It's the reason why modern electric motors in cars are vastly more powerful than older generation magnets and motors. Lightweight, well, give it a try. That's the only way to do it. You roll it off, exactly what you...
That's right.
That's it, that's the only way. Oh. That's another magnet. Now, obviously, the grade and the quality of what we call the motor system, the magnet, is significantly important to the outcome as well. There's no point making a highly stiff cone if you then try and encumber it with a low quality motor that doesn't have full control. So we specify the magnets themselves, we then magnetize them ourselves, because clearly unpacking a box full of those when magnetized would be a barrel of laughs.
So we magnetise them ourselves first, which is just done over there. And then they're going into the complete system, as you can see, and being built up and tested right now.
When did you start using neodymium?
Oh, years ago, yeah. So first off with high frequency, and then gradually over time it's kind of expanded outwards. Clearly it's expensive because it's rare earth material. So our more affordable loudspeakers, it tends to be only used in the high frequency. In our mid-tier, it's used in the high frequency and the mid-range, and then in an 800 we're using it pretty much everywhere.
Okay.
Because of the cost.
What other materials have you used for the magnets?
Well, traditional ferrites, good old-fashioned cast iron magnets. I mean, they're still quite successful, still very capable. This is optimal, but much more expensive. The interesting thing on that front is we're already starting to look into how, going forward, we could try to recycle magnets more effectively, because it is a very rare earth material and it's in high demand. So,
This is what Lister helped source.
yeah, exactly. Conversations around that right now. Exactly. Polishing over there. So this is taking that cabinet that you saw before, and
Yeah.
you can see it's smooth, but at the point now it's dull, right?
Yeah.
So what the guys are going to do is machine polish it to bring out the sheen. So it will go through a 70-odd minute cycle time in there, where it's being polished to a high standard.
Yeah.
And then when it comes out this end, the guys will check it in exactly the same way as they would check anything else. Obviously, as you saw, person working together again. And that gives us the final finished quality, which, as you can see over there, is pretty spectacular. So just see you right there, Warren. So
Oh, right.
Yeah.
Yeah. Oh, yeah.
Yeah, this is the thing. As we go through them, basically, they start life as wholly wooden cabinets with little bits of metal on them, and by the time they've got to the end of the line, it's probably about 40% metal. Particularly on one of these bigger ones. This is an aluminium bottom plate as well as an aluminium top plate. It's got a spine. It's got the sections inside, as you can see, that are metal. It has aluminium pods that go into it, and then there's an aluminium turbine head and a tweeter body. So it's a really significant proportion of the overall cabinet. But obviously, as we said right at the start, the main bit that you might have a wood finish on has to remain wood. So
How much are these a pair?
£32,500. But you do get two.
You do get two, yes. Okay, good.
You see these sections right here in the top of the cabinet.
Yeah.
See these loose sections here?
Yeah.
So later on down the line, the guys are going to be putting a head assembly on top of this, and it's going to rest on very low shore hardness mounts, rubber mounts, that are essentially making sure that the head is isolated from the cabinet. If you think about how vibration works, and again, the perfect example would be take an orbital sander and put it on a wooden floor, and the whole floor starts vibrating in sympathy. This cabinet's putting a lot of energy out,
Yeah.
and that energy is going to go down into the floor, and it's going to go up into the structure. And if it goes up and goes into the mid-range, then the mid-range will be reacting in response to that vibration. Even worse if it goes upwards into the high frequency. If you think about going on a fairground ride and you get spun around all over the place and it feels like your eyes are rattling in your head in the process, same kind of thing. What we want to make sure is that the Diamond Dome is completely isolated from those unwanted effects. And this is the first step in the process of doing that.
Right.
And as we go down, you'll see the rest of it. This one, you see it's got a damping sheet there, see where my finger is? And then it's got a steel plate on top. Not so easy to lift up. Now,
Oh, wow. Yeah.
dead. So that's the fit out. There's this Tech Sound damping sheet. I'll get out of her way. There you go.
Sorry.
That's all right. Just about to go in.
Oh, I hate cameras. Oh my god.
Drive units. They'll go into, in this particular case, a pod like that, which, as you can see, is an aluminium extrusion. Very high quality component part indeed. So that's just machined off and then radial anodized diamond cut bright edge. And then this part right here is bolted into position into the cabinet here. So remember we said before there's an aluminium plate on the inside, if you remember? So the aluminium plate provides that coupling for the aluminium pod. So that's bolted through the wood and then done up really tightly into compression. And then the result of that is massive stiffness around here. Now you'll notice fingerprint marks and so forth. The reason is, as you can see, all the operators, you want to capture this by the way, Alan, work barehanded. That's a compressed air handler. I love that toy.
Oh, wow. Yeah.
Lifting 80 odd kilograms of compressed air.
Yowza.
So yeah, beyond, once you get to this final stage, then gloves come out. But up until that point, when guys are assembling component parts, we don't want anybody to have the risk of dropping something. And we haven't yet found a glove that's as effective as the human hand. So we actually accept a little bit of DNA and fingerprints here, because we can clean it off here. And it's much more effective than risk of damage through droppage. But when you come to the final cleaning process, as you can see, now we're in the world of gloves and perfection, right? So going down this end. Right, Joe. There's that top plate that we saw from before. And then the next stage is building up all the different elements that go onto it. So you can see the leather collar section that's going to go on there like that. You can see the turbine head assembly, which is going to go in position. And the drive unit's right there as well. And we're into the world of black mirrors right now, right? Now, remember me saying, guys, this section here is isolated from, and as you can see, we'll move here, see? Isolated from this on those low shore hardness mounts. And this section is also isolated from here. So all those different decoupling elements are a key, like I said, to making sure that each one of these cones works perfectly.
Decoupling the decoupler.
Yeah. I'll hold on to that one. That's more straightforward. There you go, got it? Yeah.
It's crazy.
The cone itself is also decoupled inside the assembly. So here, see there's a small amount of movement on it?
Yeah. Yeah.
So there's a sprung rod that runs through the center of the system right there.
Yeah.
And the whole motor system is essentially slotted onto that sprung rod and then essentially floats as best we can inside the housing.
The two woofers are doing the same thing?
Yeah, they're operating in the same band, yeah, and the whole frequency enclosure is open to them. So this is separated as a separate volume, that's separate as a separate volume. This is one volume all to them, operating in the same band. Right, then last part of the process, once the guys have finished all this, is it's going to go around here and it's going to go into test and measurement. And you can hear just going on in there, Warren, if you listen. Can you hear that deep sweep?
The sweep, yeah, I heard it, yeah.
That's it.
I know it well.
So that's the final process of testing, making sure that they're doing what they're supposed to do. So this is the first time a complete loudspeaker is being measured. Don't forget all the various stages up until that point. The individual bits have been tested several times.
Yeah.
But this is the first time the whole loudspeaker has been put together and tested. So cabinet plus bits, microphone at the back.
Yep.
As you heard,
What
simply.
mic, do you know?
I don't actually. Good question. Not so knowledgeable on mics.
What do you think?
Probably an earthworks.
I was about to say an earthworks, yeah. Go in there, it's 57.
The chamber itself is constantly monitored and recalibrated. So we have, if you can see just past here, Warren, look at the units at the back that are in that kind of battleship grey colour.
Yeah.
They are the individual line references for the models that are being made along this assembly line. So they're the ones that have essentially been signed up by the chief acoustic engineer as referenced quality stock, and they live on the end of the line, and then the chamber is periodically recalibrated to them to make sure that what we want to make is what we expect to be making.
Incredible.
Only at this point, and Joe's doing it right there, will the serial number be lined up to it and with a little tag that says pass test, and only at that point does it go forward to here to be cleaned.
And how much are these ones again?
£32,500
For a pair.
for a pair.
And the amps that go with them?
Oh yeah, I mean realistically on this level you're in a world of probably 50k by the time you've done the amps and the speakers together.
So like 18k more for the
Yeah,
amps?
yeah. Oh well, power handling, I mean they can,
Yeah.
they can handle up to a kilowatt,
Oh, okay, wow.
no problem. I mean power output really depends on
efficiency of
and
the
how you're listening and the size of the room and what you're listening to and lots of other variables.
Yeah.
I mean, essentially, you'd be wasting your money if you tried to connect those up to a 30-watt amp from, you know, that you found in the loft. They require a bit of authority.
Right.
They've got some really deep, substantial output. I mean, you're going to hear a pair of these later on. They're definitely
Great.
fun. Yeah. And so last part, final cleans, final checks, all the rest of it. And then we drop them into the box. Again, not drop, lift using the air handler. And there's a pair good to go.
Sort of reminds me of early jet technology.
There's something very Harley Earl about it. If you're interested in 1950s, 1960s cars, Harley Earl was the stylist who decided that it would be a great idea to kind of weld 1950s jet fighter tropes onto American cars.
Sure.
So that's when Cadillacs acquired all those fins and those turbines and all that other stuff.
Yeah.
I think especially here, it's a bit Buck Rogers, isn't it? There's a bit.
Sure.
But yes, we're very pleased with them.
They're beautiful.
Okay.
Now I want to hear them.
Now you want to hear them. Bye.
Andy, thanks ever so much.
Thank you very much.
That was marvellous. Now, any of you watching will notice we're sitting here, actually, either side of a beautiful pair of speakers, which, if you stay tuned or actually go over to Mr. Christian Coller's channel, you will hear him interviewing Andy. They did sit down in here, in fact, we all did, and listen to a whole bunch of amazing music. And they're very impressive, these speakers.
Great stuff. Good to hear.
Could I just load them in the back of the car and take them home?
Absolutely, go for it.
Okay, cool. Thanks, everyone. Stay tuned. Go to Christian's video. There will be a link down below. So long, farewell, have you desire, au revoir, adios, tschüss, goodbye. Two scenes.